So next up, we have Jialu from Cornell University, who's going to talk about Bluebell.
Hi. Before you guys can go to lunch, I want to tell you about our paper, Bluebell, an alliance of relational lifting and independence for probabilistic programming, for probabilistic reasoning. My name is Jialu. I'm a PhD student at Cornell University, and this is a joint work with Emanuele at University of Konstanz in Germany and Azadeh at University of Toronto in Canada. Our work situates in the space of deductive verification of probabilistic programs. So the overall goal is to try to prove a probabilistic program satisfies some specification. And in this space, existing techniques can be roughly divided into two camps. The first camp is unary reasoning, where one proves property of a single program. And the second camp is relational reasoning, where you are concerned about how two programs compare to each other. So you would compare the two programs and their outputs. With Bluebell, we identify a small set of a small but expressive set of reasoning principles from which you can recover reasoning principles for both unary reasoning and relational reasoning. And because we provided a unifying foundation for both unary and the relational reasoning, in our framework, you can mix these two styles of reasoning together. And not only that, because we have both of them, we also identify some new reasoning principles that unlock new proof strategies. In this talk, I'll first overview some existing techniques in unary and relational reasoning space, and then try to advocate why you want to mix them together through a simple example. Last, I want to touch a little bit about how we do that. So when you want to prove a unary goal, a current state of art or in technique in the community is probabilistic separation logic. Let's see how it works in action through a small example. So here, this is the program for one-time pad encryption. You have some message drawn from some distribution. Here, the message is a Boolean, and it can be drawn from any distribution over Booleans. And we want to encrypt that into a ciphered message C and ensure that knowing the ciphered message does not tell you anything about the original message M. And this specification can be expressed as the independence of the original message M and the ciphered message C. In terms of probabilistic separation logic, this condition could be expressed as this assertion. As in other variants of separation logic, there's a star, which is an additional conjunction added to the first order logic. And in probabilistic separation logic, the star is used for asserting probabilistic independence. So the reasoning of this program will proceed as the following. In the beginning, we start with a trivial precondition. After the first sampling, you know that M is distributed as such. You can do the same for the second sampling if you start from the trivial precondition. In probabilistic separation logic, there's the frame rule, which allows you to do reasoning more modularly, which says that if you can prove that starting from a precondition phi and run a program C, then you can always end up with a postcondition psi. Then suppose you instead start with a stronger precondition, saying that you not only have phi, but have some independent fact, alpha, and this C does not touch alpha. Then in the end, alpha is still valid and is also still independent from the postcondition psi. And people often call this alpha the frame. And here we can treat the assertion M distributed as flip 0.7 as the frame and put them here. And this gives us this assertion after the two assignments. And that is enough for guarantee that if we take an XOR of M and K, C is independent from M. If the last step sounds mysterious. Don't worry, I'll come back to that later. But yeah. But sometimes the goal that you are interested in may not be unary. Maybe the goal you are interested in is that two programs are equivalent. Then in the community, people have also developed techniques for reasoning about programs relationally. And there are like a few talks on that as well, just at this conference. And the key idea is that you can reason about two programs in lockstep. Here I have like two very simple programs. And in the following, I'll use angular brackets to denote the index of the program. So this is program 1, and this is program 2. In this case, assume that B is the same at the beginning of the programs for these two programs. Then we can reason in lockstep that after the first assignments to X, we have X at program 1 equal to 1 minus X, 1 minus X at program 2. And in the end, we have Y at 1 equal to Y at 2. This is nice. And then what if we have the program draw samples from distributions? In the previous case, we aligned the program execution perfectly in lockstep. But when the program makes samples, then there's not only a single program trace, there are multiple ones, and the samples from one of them probabilistically. A cute idea also from the community is called the coupling method, which says that we could correlate the execution of these two probabilistic programs so that to make it easy to pair together their program traces. And in this case, we can correlate them by flip a coin in the background, a fair coin, and assign its result to B. And instead of drawing samplings in program 1, we assign B to X. And similarly, instead of drawing sample at program 2, we assign 1 minus B to X. In this case, because B is drawn from a fair distribution, 1 minus B is also fair between 0 and 1. And if you only look at one of the programs, you will notice that we haven't changed the distribution, the output distribution of the program. But now we have paired together the possible traces of these two probabilistic programs such that we can reason about them in lockstep. So we can proceed with a similar reasoning, which would show that we have paired together the program traces such that in each pair, in the end, we have Y1 equal to Y2. Notice that here, what I wrote are assertions for pairs of deterministic program states. But the whole sentence I just said that we can correlate the two programs such that we match their traces, and so that each of them satisfy these assertions. This is assertion on pairs of probabilistic distributions. In the literature, they denote this using, they call, we in this talk will denote this using the floor brackets. And in the literature, this kind of assertion is called relational lifting. The cool thing is that a lot of interesting properties about pairs of distributions can be encoded through this through relational lifting. For example, the distribution equality can be encoded as the relational lifting of just this equality. So in this case, from this relational lifting, we can infer the distributional equality of Y1 and Y2. So we've seen a little bit about both unary reasoning and relational reasoning, and they seem to be very different. It might be unclear why we want to mix them and how we mix them. And next, I'll show through a simple example that claim that we miss some opportunities if we do not have them together. So here are two other programs, which are also very simple. If you look at them, both of them draw samples and assign to x and y. And y in both programs are drawn from the same distribution. Similarly, x in the two programs are drawn from the same distribution. And x and y are independent at program 1, and x and y are independent at program 2. So intuitively, output distribution of program 1 and output distribution at program 2 should be the same. So one question is that, can we establish this relational lifting in lockstep? The problem is coupling method requires proving in lockstep. So here, if we align the two programs as before, then after the first line at the two programs, there's nothing interesting we can establish about the x at 1 and the y at 2, because they are drawn from different distributions, and it's hard to correlate them in an interesting way. We can align them differently. For example, align the two x together and construct and show that we have this relational lifting, from which we can infer that x at 1 and x at 2 have the same distribution. We can also align them in this way, which show that y at 1 and y at 2 have the same distribution. However, can we infer from the fact that we can prove both relational lifting, that we can combine them into one relational lifting? This is unsound. But in our intuitive reasoning, we use the fact that x and y are independent. So in this case, actually, if we can prove that we can use independent resources to construct a two relational lifting, then we can actually combine them together. And independence is inherently a unary property. It doesn't make sense to talk about independence between two variables in different programs. So this rule only makes sense if we mix unary style of reasoning and relational style of reasoning. So next I'll proceed in the unary reasoning side. I've first shown you some reasoning about independence. And there are follow-up works to extend that to also prove conditional independence. On the relational reasoning side, for probabilistic programs, people have used relational lifting. And our observations is that relational lifting looks awfully like conditioning. And we unify them into what we call the joint conditioning modality. For the unary case, now I'll quickly go through how joint conditioning works for the unary case. Suppose we have some distribution that satisfies this assertion. So it says that x is a fair coin, and the fact that y and also y is always equal to 1 minus x. What if we condition on x? In this case, it's simple. If we condition on x, then with probability 0.5, then we have x equal to 0, and this fact holds because it always holds. And also with probability 0.5, we have x equal to 1, and this holds still. In terms of our conditioning modality, we can rewrite this formula as this thing. So the flip 0.5 here comes from the fact that we're constructing this distribution, and x equal to v is just an abbreviation because we want to combine these two branches. And this is the same. For the relational case, so first, I just copied over what I had from the last slide, but I added the index because now the variables are all referring to variables at program 1. And to continue from our example in the coupling case, I would assume that at index 2, we have some distribution satisfy this assertion. Again, we can do a case analysis of the second distribution. So like, if we want to condition on x at that distribution. And one way, and the case analysis would say that with probability half, we have this assertion hold, and with probability half, this other assertion hold. And so what we want here in the relational case is to condition x1 and x2 together. I would say there are many ways to condition on them together, but one way that, okay. One way to condition them together is what we showed in our coupling proof, that would relate x at 1 and x at 2 together. This joint conditioning modality satisfies a lot of useful and expressive rules with which we can derive all rules in probabilistic relational Hoare logic, and also new principles for derived relational liftings, such as the one I showed before. And this is another example. And also, unary reasoning becomes more powerful. Recall the example I showed in the beginning. In previous paper, they need to use ad hoc axioms about XOR to bridge this gap. But with rules for the joint conditioning, we no longer need those custom axioms. In the paper, we included more examples. And also, I want to comment that the research doesn't come into vacuum. In the community, there have been a long line of research in probabilistic relational logic. And the idea of using the coupling method and encode this in program logics comes from this POPL' 2009 paper. And the idea that that assert independence using separation star comes from this POPL' 2020 paper. And our joint conditioning modality was heavily inspired by POPL' 2023 paper, which introduced unary conditioning modality to encode conditional independence. So if you're interested in our paper, feel free to scan this QR code. And also, my collaborator, Emanuele, is hiring students in Germany. Yeah.
Thank you, Jialu. Any questions?
Thank you for the talk. It's very cool work. Can you go back to the slide where you show the relational version of the joint conditioning modality?
This one?
Yes.
Okay.
Can you explain how the binders rule work? Like the V is bound to the flip 0.5?
Oh, which one? This line?
That one, sure, yeah.
How do I write, am I writing this? Or?
I guess the question is, so on the top you have two flips.
Yeah.
But on the bottom you have just one flip that is bound to the variable V. Right, so is this...
could you ask your question again, sorry?
Yeah, how does the conditioning modality bind the V to the two flips?
So
that here, I guess you want them to couple them, right? Is that the point?
Yeah. So in this case, so first let's start with the unary case. We bind V to this distribution. So V is sample from this distribution, and X is equal to V. And this is equivalent to condition on X. The assertion you make here are true if you on the distribution condition on X. And in this case, V is sampled from this distribution. But we can, assert things like both between V and variables at program 1, and also between V and program and variables at program 2.
So, okay, thanks. So if you had, I mean, normally when you have a coupling, you compute some kind of joint distribution and you sample from this distribution.
Yeah.
So could you do this in your setting instead of just?
Yeah. So here this is one way to rewrite these tuples of assertions. There are other ways to rewrite them, and another way is say that we put another distribution here, which is like you flip two independent coins, and both of them are fair, and then you'll get two variables VW, and you can use VWs at different places in the assertion here.
Okay, thank you. I think I got it.
Okay.
Yeah.
One final question for lunch.
There's a question there.
So do I understand right that if I want to prove a relational property using this, it's not that there's like a specific relational judgment, it's that I have to sort of show that conditioning on a bunch of background variables that I'm introducing, the statement just holds? Or how do I actually get my sort of relational property proven?
Yeah, so if you can do the proof in traditional like probabilistic relational Hoare logic, because we derived all their rules as well, you can just do all the proofs in that style. But we provided, so in our logic, we define this relational lifting through conditioning modality. So it provides you other ways to establish that relational lifting. Does that answer your question? Okay.
I think we're out of time.
Okay.
Thank Jialu again.
Thank you.